The expansion of the universe is one of the deepest discoveries of modern cosmology. Since it was recognized that galaxies are moving away from each other, astronomers have tried to accurately measure the speed at which the cosmos expands today, a value known as Hubble's constant. If you like this content, do not forget to subscribe and give like. This number not only describes the current rate of growth of the universe, but also allows you to rebuild its history, estimate its age, and test models on the matter and energy that make it up. However, the measurements of this constant do not coincide. Early universe-based methods offer systematical lower values than those obtained from observations of the nearby universe, such as supernova or galaxies. This discrepancy, known as Hubble's tension, has become one of the most important open problems of cosmology. A new paper now proposes a different strategy based on gravitational waves that could provide independent information to clarify this conflict. Hubble's constant, denoted as h0, describes how far the distances between galaxies expand for each megaparsec of separation. In simple terms, it indicates how fast the universe is growing today. The most precise measurements come from two main approaches. On the one hand are observations of the early universe, especially of the cosmic microwave background, which capture the state of the cosmos about 380,000 years after the Big Bang. On the other hand, there are methods based on relatively close objects, such as Ia-type supernovas, which function as standard candles to measure distances. Both approaches should converge on the same value of h0. However, this is not the case. Estimates of the early universe tend to be about 67 to 68 kilometers per second per megaparsec, while measurements of the late universe point to higher values, around 72 to 74 kilometers per second per megaparsec. Some researchers interpret this discrepancy as a possible indication of new physics, perhaps related to dark energy, unknown interactions of dark matter, or phenomena that affected the primitive universe. In the last decade, direct detection of gravitational waves has opened up a new way of studying the universe. These ripples of space-time occur when extremely dense objects collide with each other. The new study introduces a different strategy to take advantage of the information contained in gravitational waves. Instead of analyzing only the individually detected fusions, the gravitational wave background is also considered. Medium-term prospects are especially promising. As gravitational wave detectors increase their sensitivity, the gravitational background is likely to be detected directly in the coming years.